Binary acids, the compounds we placed in quadrant 4 on our nomenclature grid. Acids need something to accept the hydrogen. If the material is pure, it has nothing to accept the hydrogen, and so it doesn't really act like an acid. It acts more like just a normal binary non-acid. On the other hand, if it's mixed with water, water can actually accept that hydrogen, and so it really is acting like an acid, and so it's named as an acid. So to illustrate this dual nature, let's consider HCl. An aqueous solution of HCl is called hydrochloric acid. Now remember, chloric acid was HClO3. So one way to kind of remember what HCl is just to pretend it loses every one of its oxygen. What's left? HCl. We still keep the chloric acid name, but we just add hydro in front of it. Let's do another one. We know H2SO4 is sulfuric acid. If we take all of the oxygens off, we're left with H2S, and so we would call that hydrosulfuric acid. So when HCl or the binary acids are in water, you name them as an acid. But what about we're in the pure solid or pure liquid or pure gas form, as noted by the letters S, L, and G? Well, then they do not act like an acid. They act more like binary non-acids. So pure HCl, named as a binary compound, would be hydrogen chloride. H2S, by analogy, would be what? Hydrogen sulfide. That's the common name. If you called it dihydrogen sulfide, I would certainly give you credit for that as well. And you might ask, well, what if I'm not told if it's aqueous or a solid or a liquid or a gas? What if I'm just given HCl? And the answer is either one of those two answers is correct. You're allowed to assume it's an aqueous solution, or you're allowed to assume it's a pure substance. So for binary acids, if they're aqueous solutions, if they're in water, you name them as a derivative of the quadrant 3 polyatomic acid name. And if they are pure substances, you may name them as the binary non-acid.